let's say I have a battery in my circuit. Okay. Say we have a battery. Now the battery can be modeled like this. We could have a voltage source on the inside of the battery, and we can have a little resistor which we call internal resistance. So this little voltage source on the inside we call EMF. EMF stands for electromotive force. This is more a historical thing than anything else. Back before they knew what was going on with atoms and electrons, they just knew there was something pushing the charges through. Something was pushing it through. And so they called it an electromotive force, a force pushing electrons, okay, through the circuit, moving them around the circuit. So you'll often see this written as just simply epsilon. The units, though, are just volts. So this is just like a mini voltage source inside. Now this is called our internal resistance. And that's just basically based on the battery itself. So the battery has some resistance to it inside of it. We call that internal resistance. And the last little thing is, if I were to take a meter, which we call a voltmeter, and test across the terminals here, the negative and positive end of the battery, we would get what's called a terminal voltage. And basically that's just like it sounds, the voltage at the terminals. Okay? Now the terminal voltage can change. The EMF will not change, the internal resistance will not change, but the terminal voltage can change. Okay, so let's see just kind of how this might play out. So let's say we're going to hook up a battery. Let's say the EMF is 1.5 volts. Is connected or hooked up to let's say a 50 ohm resistor. And when we hook it up, we find that its terminal voltage is 1.3. So a question I might ask you is, what is the internal resistance? What's the internal resistance of the circuit? Okay, so let's draw this circuit out. So we're going to have our EMF source, that's right here. We're going to have our internal. So this EMF was 1.5. This is our internal. Okay, and this is like our battery, right? So if you imagine, oh, this is our battery right here. Okay, we're going to hook it up to our resistor of 50 ohms. So the terminal voltage means that's the voltage from here to here. So the voltage across the battery would be from here to here, which means that's the same as the voltage from here to here. Okay? So the voltage across a resistor, if we were to take a meter, measure the voltage across this, we would get 1.5 volts. So before we find R internal, what other piece of information could we find? We could find the current through the 50. So let's find the current through the 50. How are we going to get the current through the 50? Oops, I just did that wrong. Okay, 0.03, is that confirmed? So that's the current through here, 0.03 amps moving through there. Well, notice when you look at this circuit, what kind of circuit is this? A series circuit, right? So if we know the 0.03 through the 50, how much current is going through our internal? 0.03. So there's going to be one current going all the way through the circuit, right? 0.03. Okay, our ultimate goal is to get our internal. We know the current. What else do we need to find before we can get our internal? The voltage across our internal. So we're looking for this. Voltage across this. Well, Kirchhoff's voltage law says when you add up all these voltages in a loop, they should add up to 0. So this should be 1.5 minus this minus, oops, I wrote something wrong, didn't I?
Yeah, it'd be 1.3.
Ooh, nobody caught that? Okay, 1.3, 1.3, so 0.0, seeing if you guys would catch it, but nobody caught it. 0.026. There we go, 0.026. Okay, do you guys understand the mistake that I made? So the EMF was 1.5, but the terminal voltage was 1.3. So that's 1.3 here. So anyway, 1.5 minus our V across this minus 1.3 should equal 0. Therefore, what should this voltage be? 0.2. So this should be 0.2 volts across here. Another way of looking at it is these two voltages should add up to the 1.5 volts that we got. Alright, how do we finish this up? If we know voltage, we know current, what do we do next? Okay, we'll use Ohm's law again. V equals IR, or R equals V over I. So we're going to use 0.2 divided by 0.026. 69. So that's our internal resistance. Just one concept with the internal resistance. Notice that the terminal voltage, that's what you want. That's what you want to get out of the battery, right? As you increase this resistor, what's going to happen to the terminal voltage? the larger the resistor, it's going to start taking away more of the voltage, right? Right now they're splitting them up. This is getting 1.3, this is getting 0.2. If this was 100 ohms, it's going to take away more voltage than the 0.2. On the other hand, if this was smaller, I mean, what if this was identical? What if this resistor was 7.69? How would they split up the voltage? 50-50, right? They would each get the same amount of voltage, and your terminal voltage would be much less, okay, like about half, than what you would want to get. Okay.